Imagine you are looking at a photograph, like just a regular digital picture on your phone.
Right, okay.
And there's this tiny, microscopic blemish right in the dead center of it.
Like a dead pixel or something.
Exactly. So your immediate instinct is to pinch the screen, right? To magnify it.
Yeah, you want to zoom in and see what's going on.
Right. And you zoom in so closely, expecting that eventually, you'll just see the underlying pixels.
You expect to hit the bottom of the image, basically. The flat, blocky reality of it.
Exactly. But imagine if, when you zoomed in on this specific blemish, instead of finding pixels, you fell into an entirely new hidden dimension.
Oh, wow.
Yeah, like you zoomed into a single flat dot, and suddenly you were looking at a vast, infinite line stretching out in front of you.
That's a crazy visual.
It's wild, right? And this line contains a whole universe of structural information that was, like, completely invisible from your original top-down perspective.
Completely hidden.
Yeah. So, welcome to this deep dive. We are speaking directly to you, the Bussin Sigma scholars of Edward Little High.
We know you guys have that intense academic curiosity.
Right, the kind that isn't satisfied with surface-level explanations. Which is exactly why we are taking a journey today into one of the most mind-bending concepts in algebraic geometry.
It really is mind-bending.
Okay, let's unpack this. Our mission today is to look at a specific, problematic mathematical object.
A very specific one.
Yeah, it's a plane cubic curve defined by the equation minus 6 Celer squared times the quantity 6 plus 1 equals 0.
Right.
And we are going to figure out how to mathematically perform surgery on it, basically, to fix a fundamental flaw right at its center.
It's a phenomenal thought experiment, honestly. And I am thrilled to explore this with you all today.
It's going to be fun.
Because that transition you just described from a dimensionless point into a fully realized geometric line that is the absolute definition of a mathematical paradigm shift.
For sure.
We actually call this operation a blow-up.
A blow-up. I love that term.
It's very dramatic. But to give you a sense of our trajectory today, we are going to basically act as geometric detectives.
Okay, I like that. Put on our detective hats.
Exactly. We need to diagnose exactly what is wrong with this curve at the origin, figure out the trajectory of its crashing branches.
Right, map a crash site.
Then mathematically invent a new spatial dimension to untangle that crash. And finally, we have to rigorously prove that our dimensional surgery actually, cured the underlying disease.
Okay, so I want to start with the disease itself. Let's look at our patient.
Let's do it.
We have the curve, a Udasalt squared minus 6 squared times 6, 1 equals 0.
Right.
And just to make the algebra a bit more intuitive as we go, if you distribute that 6 squared through the parenthesis, we're looking at the polynomial Yale squared minus 6 Glauer squared minus $6 cubed equals 0.
Much cleaner to work with.
Yeah, definitely. Now, I've seen a graph of this thing. If you plot it out, it looks a bit like the Greek letter alpha.
Like a ribbon that's been tied into a simple loop.
Exactly. There's this smooth curve looping around on the right side of the graph. But right at the origin, right at the coordinate 0, 0.
Your dead center.
Right. The line crosses directly over itself.
And that crossing is the core of our problem today.
Because it's not smooth.
Right. In mathematics, and particularly in algebraic geometry, we have a deep, deep appreciation for smoothness.
Makes sense.
When an algebraic curve is smooth, it behaves predictably.
Like driving on a freshly paved highway. As long as the road is smooth, at any given millisecond, your car is pointing in a specific, definable direction.
Exactly. There's a clear tangent line.
Right. So if you freeze time, you can draw a straight, unambiguous arrow showing exactly where the car is heading.
Yes. And mathematically, that forward direction is guaranteed by something called the implicit function theorem.
Okay. Assuming what?
Well, provided that the gradient of the function defining the curve doesn't vanish.
Right, the gradient.
Yeah, the gradient is essentially a vector made up of the partial derivatives of our function.
So just taking derivatives with respect to 6 and I.
Exactly. So if we take the partial derivative of our polynomial with respect to 6n, and the partial derivative with respect to 6n's, at least one of those values must be non-zero at any given point.
For it to be smooth, right?
Yes, for the curve to be smooth. If you have a non-zero derivative, you have a defined slope. You have a tangent line.
But I'm looking at our origin point, right?
Zeros.
0, and I can see the problem visually.
It's a mess.
Yeah, if I'm standing exactly at the epicenter of that intersection, right where the two roads cross, and someone asks me, Which way is forward along the curve?
You can't answer.
I honestly can't. There isn't one forward direction. The structure has basically tied itself in a knot.
It really has.
But what does that actually mean when we crunch the numbers? Like, how does the algebra reflect that visual chaos?
Well, the algebra reflects it by essentially throwing its hands up in the air and returning nothing.
Oh, really?
Yeah. If you take our function, it goes squared minus 6 squared minus 6 squared minus 6 cubed, and you calculate its partial derivatives, you get a gradient vector.
Okay, let's do the math.
So the derivative with respect to 6 squared becomes -2. 6 bowls minus 3 6 squared.
Got it. And the derivative with respect to dollars is simply $2.
Right. Basic power rule calculus.
Yes, standard Calc 1 stuff.
Precisely. What happens when you evaluate that gradient specifically at the origin, where both 6Ls and L's are 0?
Well, the 6 deck component becomes 0 minus 0, so just 0.
Yep.
And the ala component is 2 times 0, which is also 0. So the entire gradient vector is just 0, comma 0.
Exactly. The derivatives vanish completely.
And that vanishing gradient is the mathematical signature of a singularity, isn't it?
It absolutely is. The geometry is telling you the road crashes into itself, and the algebra confirms it by just failing to provide a tangent vector.
It just gives up.
Pretty much. The rules of calculus literally break down at this specific coordinate because the curve is occupying the exact same space from two entirely different trajectories.
Okay, so we've diagnosed the singularity. It's a crash site.
A bad one.
But not all crash sites are the same, right? I mean, some are head-on collisions, some are side swipes.
Good point.
We need to classify just how bad the singularity is. And I know mathematicians use the term multiplicity for this, right?
We do, yes.
But how do we extract that from the polynomial without just relying on looking at a graph?
We look at the polynomial through a very specific lens. We basically group the terms by their total degree.
Okay.
In our equation, y squared minus 6 squared squared minus 6 over cubed equals 0, we have terms of degree 2.
Which are the squared and the negative 6 squared.
Right. And then a term of degree 3, which is the negative 6 story cubed.
Okay, so we have degree 2 and degree 3.
Exactly. To find the multiplicity of a singularity situated at the origin, you simply identify the lowest degree of the non-zero terms present in the polynomial.
Wait, really? We just completely ignore the higher powers. The 6-scholar cube just doesn't matter for this classification.
It doesn't. Near the origin, where $6 are incredibly tiny, fractions of fractions, higher powers shrink much faster than lower powers.
Oh, I see what you mean.
Imagine $6 is 0.1. The square of that is 0.01. But the cube is 0.001.
Right, it gets smaller way faster.
Exactly. So infinitesimally close to the singularity, the lower degree terms completely dominate the geometry of the curve.
So the higher degree terms are essentially just background noise.
Exactly.
That makes perfect sense. So looking at our lowest degree terms, y squared, and negative $6, they are both degree 2.
Yeah.
So the multiplicity is 2.
Correct. We call this a double point. Intuitively, the multiplicity tells us how many branches of the curve are passing through that single chaotic point.
So 2 branches are colliding.
2 branches are colliding.
Okay, so 2 branches are crashing. But to really understand this intersection, I don't just want to know that they're crashing.
You want details.
Yeah, I want to know the exact angles of the impact. I want to know where they came from and where they're trying to go.
And that requires finding what we call the tangent cone.
The tangent cone.
Right. What's beautiful about this algebraic method is that the very same lowest degree terms that gave us the multiplicity, they also hand us the equations for the tangent lines on a silver platter.
Oh, really? How does that work?
We take that dominant lowest degree part of the polynomial, the y squared minus $6 squared, and we isolate it by setting it equal to 0.
Setting Gauss squared minus 6 squared equal to 0, well, that's just a classic difference of squares.
Exactly.
So if we factor that, it breaks down cleanly into the quantity y minus $6 multiplied by the quantity all plus $6 equals 0.
Perfect. And because the product equals 0, we can set each individual factor to 0.
Okay, so that yields 2 distinct linear equations.
Right.
Minus $6 equals 0, which simplifies to the line y equals $6, and y equals 0, which gives us the line y equals negative $6.
That is incredibly elegant, isn't it?
It really is. By just zooming in on the dominant algebraic terms, we instantly discover the trajectories of our 2 branches.
Exactly.
So the line equals 6 has a slope of 1. It cuts through the origin at a perfect 45-degree angle.
Right.
And the line equals negative $6 has a slope of negative 1, cutting through at a 135-degree angle.
Yes. And together, these two lines form the tangent cone at the singularity.
Okay, I can visualize that.
And in our specific case, because the two tangent lines are entirely distinct, they have completely different slopes, we classify this singularity as an ordinary double point.
Or a node, right. I think I've heard that term.
Yes, more commonly known as a node.
A node. So visualizing the alpha-shaped ribbon, again, at the origin, we have a road coming from the bottom left crossing a road coming from the top left.
Correct.
They smash into each other perfectly at 0, 0, with distinct slopes of 1 and -1, forming a perfect X, and then continue onward.
That is the exact geometric reality. You have two distinct branches, an alpha branch and a beta branch, if you will, crossing perfectly.
Right.
But at the exact moment of intersection, the mass fractures.
Which brings us to the most crucial question of this deep dive.
The big one.
Yeah. If this coordinate is broken because two roads are stubbornly insisting on occupying the exact same space at the same time,
Right.
how on earth do we fix it? And we can't just redraw the whole curve, right?
We can't do that.
We want to preserve the geometric essence of the object, but somehow untangle the crash site.
What's fascinating here is that we solve this not by altering the curve within its current flat two-dimensional constraints.
We don't.
No, we solve it by fundamentally expanding reality.
Oh, wow.
We invent a new dimension. We perform a geometric blow-up.
Inventing a new dimension. I love how mathematicians talk about reality like it's just a sandbox they can play in.
It kind of is.
So walk me through this. How does adding a dimension untangle a 2D knot?
So, to resolve the singularity, we blow up the plane at the origin. Geometrically, this means we are going to surgically remove the single problematic point, 0, 0.
Okay, remove the point.
And we are going to replace it with an entire projective line.
A whole line.
Yes. This newly inserted line is called the exceptional divisor, and we denote it as $, which is isomorphic to pull.
Let me make sure I'm picturing this correctly. We're swapping out a dimensionless dot for an entire line.
We are. The space $1 represents the one-dimensional projective space.
Okay.
For the sake of visualizing this, you can think of the points on this exceptional divisor as representing a catalog of all possible slopes.
All possible directions.
Exactly. All possible directions of lines that could ever pass through the origin.
Okay, I think an analogy might help our Sigma scholars visualize this because it's a huge conceptual leap.
Yeah, analogies are great here.
Imagine you are standing on a glass floor at the very top of a tall building.
Okay, I'm there.
And you're looking straight down the center of a spiral staircase.
Oh, I like this.
From your top-down 2D perspective, the staircase just looks like a flat circle, right?
Yeah, completely flat.
The stairs appear to cross over each other constantly. If you try to trace a path with your finger on the glass, it just looks like a continuous self-intersecting loop. Every point looks like a crash site.
That's a brilliant visual.
Hmm.
From that restricted 2D projection, the structure appears completely singular everywhere.
Right. But how do you untangle a spiral staircase? You don't try to redraw the flat circle.
No.
You simply shift your perspective to 3D. You walk down the hallway and look at the stairs from the side.
And suddenly you see the depth.
Exactly. Suddenly you realize that the stairs that look like they were crashing are actually separated by height.
They never touch.
Right. What looks like a chaotic intersection in 2 dimensions is actually a perfectly smooth, non-intersecting ribbon when you introduce a 3rd dimension, the z-axis, the elevation.
And that spatial separation is exactly what the blow-up accomplishes algebraically. Yes. Our curve is crossing itself because both branches are forced into the coordinate 0, 0.
Okay.
But we know from our tangent cone calculation that one branch is traveling with a slope of 1, and the other is traveling with a slope of -1.
Right. We found those slopes earlier.
So they have completely different directional identities, even though their geographic location is currently identical.
So the blow-up adds a height dimension, but instead of physical elevation like the staircase, this new dimension represents the slope of the curve.
Precisely. We are lifting the curve out of the flat 2D plane and into a 3D space.
Oh.
By doing this, we separate the crash by assigning each crossing branch its own distinct vertical lane based on its unique slope.
Oh, man, that's cool.
So the branch entering with a slope of 1 will be pulled up and pinned to a height of 1 on our new exceptional divisor.
Right, and the other one?
The branch entering with a slope of -1 will be pinned to a height of -1.
That is just incredible. We are basically turning a single chaotic intersection into a multi-level highway overpass.
That's exactly it.
The cars never even touch each other. The origin was a point, but now it's a line, and every address on that line is a different slope.
It is a profound triumph of geometry. Historically, this concept, resolving singularities by blowing up spaces, was a monumental undertaking.
I can imagine.
Mathematicians like Heisuke Hironaka won the Fields Medal for proving this could be done in algebraic varieties of any dimension.
Wow, the Fields Medal. That's a big deal.
It's a huge deal.
Hmm.
But the challenge for us today is that we must translate this beautiful geometric intuition into cold, hard, rigorous algebra.
Right. Back to the numbers.
We have to compute the total transform of our curve.
Which means we need to mathematically map out all these possible slopes.
Exactly.
But here's where I get hung up.
Okay, what's the hang-up?
If we are defining a new dimension based on slope, standard algebra defines slope as rise over run, right? Dollar divided by sixers.
Right.
If we just define a new variable, say $J equals dollar divided by sixers, doesn't standard algebra completely panic if we have a vertical line?
It absolutely panics. This is a very sharp observation.
Because you're dividing by zero, right?
Yes. If a branch of a curve happens to pass through the origin perfectly vertically, the run is zero. The $6 coordinate is zero.
Right.
If you try to calculate the slope, 2all equals dollar divided by zero, the math is undefined. It approaches infinity.
It breaks.
A single affine coordinate system simply cannot capture the concept of an infinite slope. The algebraic scaffolding breaks down entirely.
So how do we map out the entire exceptional divisor all the way to infinity without breaking the math?
We use a technique similar to cartography. Think about mapping the surface of the Earth onto a flat piece of paper.
Like a world map.
Yeah, you can't make a single flat map of a globe without severe distortion, usually at the poles. The mathematics of the projection falls apart.
Right, like the Mercator projection where Greenland looks the size of Africa. It stretches infinity, essentially.
Exactly. So to map the globe perfectly, you don't use one map.
Okay, what do you do?
You make one map focused on the equator, and you make a separate map focused on the poles. Where they overlap, they agree, and between the two of them, you have the entire sphere covered seamlessly without the math ever breaking down.
Oh, that makes sense.
We do the exact same thing for the blow-up. We use two overlapping maps, which we call affine lobe charts.
I see. So chart 1 handles a specific set of slopes, and chart 2 handles the rest.
Chart 1, often referred to as the Sixelvola chart, is designed to capture every possible slope except the perfectly vertical one.
Okay, got it.
For this chart, we introduce your suggested variable. 2 equals dollars divided by $6.
Right.
To substitute this back into our original polynomial without using fractions, we simply multiply both sides by $6, which gives us the substitution key. D equals $6 times NR.
Okay, so for our first map, everywhere we see a dollar in our original curve equation, 6 scale minus 6 squared equals 0, we are going to swap it out for the quantity 6 molars times dollar.
Let's execute that substitution. When we plug in $6 for dalar, the algebra organically begins to separate the geometry.
Okay, let's see.
Instead of grinding through the arithmetic step by step, what do you notice about the resulting terms when you square the quantity $6, $2?
Well, if the first term becomes the quantity $6 times 2 squared, that's 6 squared times 2 squared.
Right.
The other terms are negative 6 squared and negative 6 cubed.
Exactly.
So looking at the whole thing, every single piece of this new equation shares a common factor.
They do.
They all have at least an 6 squared in them.
Precisely. Because every term shares that 6 squared, we can factor it out entirely.
Oh, nice.
We pull the 6 squared to the front, and what we are left with inside the parentheses is whole squared minus 1 minus $6.
Okay.
So our final equation for chart 1 is $6 squared times the quantity dollars squared minus 1 minus 6 equals 0.
Okay, that is super clean. And this equation, $6 times 2 squared minus 1 minus 6 equals 0, this is what you call the total transform in chart 1, right?
It is. But before we interpret what that means, we must complete our cartography. We need chart 2.
The jar chart.
Yes, the dart chart, to capture the slopes that chart 1 missed specifically, the vertical slopes.
Right.
To do this, we flipped the definition. Instead of rise over run, we define a new variable equals $6 divided by young.
Okay, so we're just inverting it.
Exactly. This avoids dividing by 6 call equals 0. But it means this chart will fail for perfectly horizontal lines where ya equals 0.
But that's fine because chart 1 already covered the horizontal lines perfectly.
I got it.
They overlap and cover the whole spectrum together. So for chart 2, if 5 equals $6 divided by yai, we multiply by yaller to get our substitution key. 6 equals 9 times dollar.
Yes.
We are replacing every $6 with yai times dollar.
And when you substitute y times y force into our original squared minus 6 squared minus 6 cubed equals 0, you see a very similar pattern emerge.
Yeah, let's look. The first term stays u squared.
Right.
The second term becomes minus scholar squared times the squared.
Yep.
The third becomes minus a cubed times a cubed. So this time, every single term has a squared in it.
Exactly the same pattern.
So we pull that y squared to the front, and we get y squared times the quantity 1 minus a squared minus y times cubed equals 0. That's our total transform for the second map.
Perfect. Now, it is crucial for our sigma scholars to understand what the total transform actually represents geometrically.
Okay, let's break that down.
When we perform this substitution, we didn't just passively move our original curve into a new space.
Yeah.
We actually generated an equation that describes two distinct geometric objects glued together.
Right, it's basic logic. When you have an algebraic equation formatted as $a times dollar equals 0, it implies that either the first part equals 0 or the second part equals 0 or both.
Exactly.
The total transform represents the union of those possibilities. It's like a chimera. It contains our newly smoothed out curve, and feet, it contains the brand new exceptional divisor dimensions we just pasted into the space.
Which means our next objective is extraction.
Extract.
We need to dissect this total transform and separate the newly smoothed curve from the artificial wall we built.
Here's where it gets really interesting. If we look at our total transforms, they clearly have a distinct factor sitting at the front.
They do.
In chart 1, we had $6 squared multiplying our parentheses. In chart 2, we had $9 squared out front.
Those factors are not mathematical junk. They are the keys to the entire operation.
Really?
Let's analyze chart 1. $6 squared times a quantity quarn minus 1 minus $6 equals 0. This implies the geometry is the union of two spaces. The space where $6 squared equals 0 and the space where 2 squared minus 1 minus $6 equals 0.
Well, the first space, $6 equals 0, just means 6 equals 0.
Yes, and remember that chart 1 is a 2D coordinate system using $6 0.
Right.
If 6 equals 0, that defines the entire vertical axis. It is a full line.
Okay, I follow.
That line, 6 equals 0, is exactly the exceptional divisor 8a.
Oh, wow.
It is the new dimension of slopes we created, sitting directly above the location of the original singularity.
Wait. It factored out as exactly $6 squared. The exponent is a 2.
Yes.
And way back at the beginning of this deep dive, when we found the multiplicity of the singularity, we realized it was a double point. The multiplicity was 2.
This is the profound poetry of algebraic geometry. The exponent on the exceptional coordinate factor tells us the exact multiplicity of the original singularity.
That is so cool.
The algebra remembers the geometry of the crash site. The fact that $6 squared perfectly mirrors the fact that two branches collided.
It's like a fossil record in the math.
Exactly.
Yeah.
And if you look at chart 2, where Ilioi Cathini 0 defines the exceptional divisor, it factors out as exactly squared. The consistency is absolute.
That is deeply satisfying. But as much as we love this new exceptional divisor, it's basically the scaffolding, right?
Yes, it is.
We want the actual building. We want the strict transform, which is the pure desingularized curve lifted into the new space.
To isolate the strict transform, we must logically discard the exceptional coordinate factor. We peel the curve off the scaffolding.
So, in chart 1, we drop the 6 squared. We are left with the strict transform, let's call it 6 prime, given by the equation. 1 squared minus 1 minus 6 equals 0.
Correct.
And in chart 2, we drop the just squared, leaving the strict transform. 1 minus squared minus the seed of dollars times cubed equals 0.
We have successfully mapped the lifted curve in our new 3D space.
That feels like a huge accomplishment.
It is, but our mission isn't over. The entire reason we did this was to fix the crash. We have to mathematically prove that the intersection was resolved.
Right, we can't just assume it worked.
We must locate exactly where our new, pristine, strict transform touches the exceptional divisor, $e.
Right, because if the branches still touch at a bad angle, or if they crash into each other again in this new dimension, we haven't actually solved the problem.
We had just moved it.
We just moved the knot to a higher dimension, so let's solve for the intersection points.
Let's do it.
Let's stick with chart 1. We know the exceptional divisor dollar lives exactly where $6 equals 0, and our strict transform dollar prime lives along the curve, 1 squared minus 1 minus $6 equals 0.
To find their intersection, we simply evaluate the strict transform at the location of the exceptional divisor.
So plug it in.
Exactly. We plug 6 equals 0 into 1 minus 1 minus 6 equals 0.
Okay, if $6 is 0, the equation simplifies dramatically to just if dollar squared minus 1 equals 0.
Right.
We move the 1 over, so if squared equals 1. Taking the square root, we get two distinct answers. 2 equals 1 and f12 equals -1.
Therefore, in the specific coordinate system of Chart 1, where points are addressed as $6, comma, our newly lifted curve pierces through the exceptional divisor at exactly 2 points, 0, 1 and 0, -1.
Let me just pause and marvel at this for a second. The coordinates are 0, 1 and 0, -1.
Yes,
The variable dollar, as we defined it, literally represents the slope of the curve as it originally passed through the origin.
it does.
And way back when we calculated the tangent cone, the distinct slopes of the crashing branches were exactly 1 and -1.
The mathematics is incredibly tight. The two crossing branches from the original flat plane have been successfully pulled apart in the higher dimensional space.
That's amazing.
They've been routed and pinned to the exceptional divisor at the exact geometric addresses corresponding to their original trajectories.
It's like tracking a messy ball of yarn, finding the two loose strings, pulling them taut, and pinning them neatly to a corkboard.
A great analogy.
The branch that was crashing with the slope of 1 has been routed to the height Nodal equals 1. The branch crashing with the slope of -1 has been routed to the height Uda equals -1. They missed each other entirely.
Spatially, they are separated.
Awesome.
But a rigorous mathematician never relies purely on visual intuition.
Right. We need the proof.
We must mathematically guarantee that the new curved $2 prime is actually smooth at these two new intersection points.
Oh, because we could have created new singularities.
Exactly. We need to make sure we didn't accidentally invent two new singularities while trying to fix the first one.
Okay, time to bring back the Jacobian test.
Yes.
We need to check the gradient of our new strict transform equation, 2 squared minus 6 minus 1 equals 0. If the gradient vanishes to 0, 0 at these intersection points, we've failed.
Let us calculate the partial derivatives of our strip transform dollars of $6, comma equals tax minus 6 minus 1.
The derivative with respect to $6 is straightforward. The dollar squared is treated as a constant, so it's 0. The derivative of -$6 is -1. The constant -1 goes to 0.
Right.
So the partial derivative for $6 is just a constant -1.
And for the partial derivative with respect to?
We treat $6 as a constant. The derivative of 2 squared is $2. The rest goes to 0. So the derivative for rows is $2.
Right.
Our new gradient vector for the entire lifted curve is -1, $2.
Now we test the structural integrity at our two intersection points.
Oh.
Let's plug in the coordinates of the first point, 0, 1.
The auxiliary derivative is already a constant -1. The derivative is 2 times 1, which is 2. So the gradient at the first intersection is -1, 2.
And at the second intersection point, 0, -1.
The auxiliary derivative is still -1. The u derivative is 2 times -1, which is -2. So the gradient at the second intersection is -1, -2.
If we connect this to the bigger picture, recall our very first diagnostic test.
The one that failed.
Yes. A singularity only exists if the entire gradient vanishes to 0 simultaneously. But neither -1, 2 nor -1, -2 is a 0 vector.
Right, they're not 0?
Because the gradient does not vanish at either location, the implicit function theorem unconditionally guarantees that our strict transform is perfectly smooth at both intersection points.
Yeah, did it.
We did.
We mathematically cured the curve. Which brings us to our final verdict. The Sigma scholars have followed this incredibly dense surgery step by step.
It was a journey.
So, did one single blow-up definitively resolve the singularity?
Let us synthesize the vast amount of evidence we have uncovered. First, we correctly diagnosed the plane cubic $r squared minus $6 squared times 6 plus 1 equals 0 with a node singularity at the origin.
A site where two branches collided with distinct slopes of 1 and -1.
Yes. Second, we fundamentally altered the space by blowing up the origin, replacing the crash site with a projective line of slopes, the exceptional divisor.
Right.
Third, we mapped our curve into this new reality using overlapping affine charts, isolating the strict transform.
The pure curve.
We found that this lifted curve intersects the new dimension at two distinct, spatially separated points, perfectly matching the original slopes.
And finally,
Finally, we subjected those points to the Jacobian criterion and mathematically proved their absolute smoothness.
the branches are separated, the tangents are clear, the curve is smooth.
Therefore, the ruling is conclusive.
Yes.
A single blowup perfectly and completely resolves the singularity of the nodal cubic curve. The operation was a complete success.
It is so deeply rewarding to see abstract algebra completely tame a chaotic geometric problem.
This is very satisfying.
But I have to ask, because math is rarely this universally tidy,
Sure.
does a single blow-up always work? Like, can we just apply this one magic trick to any broken curve?
That is the exact critical thinking we expect from our listeners.
I aim to please.
The short answer is no. A single blowup worked beautifully today because our singularity was a node.
Okay, a node.
The crucial characteristic of a node is that the crashing branches have distinct slopes. One was 1, the other was -1.
Right.
They were practically begging to be separated by height. But the universe of algebraic geometry is filled with much more stubborn singularities.
What's an example of a stubborn one?
Consider a singularity known as a tack node.
A tack node.
An equation for a tack node might look something like Nodal is squared equals 6L to the 4th minus 6L to the 6th. If you analyze the geometry of a tack node, you won't find two branches violently crossing each other like an X. Instead, you will find two branches that gently sweep in and kiss each other perfectly at the origin before sweeping away.
Oh, wow. If they're kissing rather than crossing, that means at the exact moment they touch, they must be traveling in the exact same direction.
Exactly.
They are perfectly parallel at the point of impact.
Precisely. They have the identical tangent slope. Now think about what this means for our blow-up operation.
Okay.
The blow-up separates branches by assigning them a height based on their slope. If both kissing branches have the exact same slope, what happens when we blow up the plane?
Oh, no. They both get routed to the exact same address on the exceptional divisor.
Exactly.
They get assigned the exact same height, so in the new dimension, they're still touching.
Exactly. One blow-up is insufficient to separate them. If you compute the strict transform for a tack node and test its intersection with the exceptional divisor, you will find that the gradient vanishes again.
It's still broken.
It is still singular in the new dimension.
So what do? Do you just give up?
You iterate. To resolve a tack node, you have to blow up the new space. You target the new singularity residing on the first exceptional divisor and you blow that up, creating a second exceptional divisor.
Oh.
And you keep repeating this algorithmic surgery, stacking exceptional divisors upon exceptional divisors until the branches finally microscopically pull apart.
That is intense.
This iterative resolution is actually a foundational concept used in advanced physics, like string theory, where physicists use blow-ups to smooth out singular orbifolds in space-time so their equations don't collapse into infinity.
That is wild. It's like zooming into a fractal, finding that the structure is still broken and having to invent yet another dimension to keep unpacking it.
Exactly like that.
But for our nodal cubic today, one single dimensional leap was all it took.
One was enough.
So what does this all mean? We started this deep dive with a purely visual geometric problem, a mathematical highway that tied itself in a knot, a point where reality seemed to break.
Right.
And we didn't fix it by guessing or drawing. We solved it using rigorous sequential algebra. By defining new variables, shifting perspectives, overlapping maps, and factoring equations, we proved that mathematics gives us the concrete power to literally invent new dimensions to untangle our problems.
That's powerful stuff.
We took a 2D crash, and we built a 3D overpass purely out of logic.
It is a profound testament to the dual nature of mathematics. We mapped a spatial geometry to a set of algebraic rules, manipulated the algebra, and the resulting equations perfectly described a new, elegant, and highly structured geometric reality.
It is arguably one of the most beautiful processes we've ever covered. But before we sign off, Sigma Scholars, we want to leave you with one final, slightly provocative geometric paradox to chew on.
Yes. We saw today that a node separates perfectly after one blowup because the crashing branches had different trajectories.
Right.
We just discussed how a tack node requires multiple blowups because the branches share a trajectory. But consider a third, completely different type of singularity known as a cusp.
A cusp. The classic example would be the curve Jerry squared equals $6.
Yes. If you plot Yelly squared equals 6 cubed, you don't see two branches crossing and you don't see two branches kissing.
What does it look like?
The curve sweeps in, comes to an infinitely sharp, needle-like point exactly at the origin, and instantly reverses direction. It consists of only one single branch, and at that sharp point, it possesses exactly one tangent direction.
Okay, so it only has one slope. It's just a single sharp needle.
Now, if you perform a blow-up on a cusp, and I highly encourage the ambitious listeners to run the algebra themselves, you only get one intersection point on the exceptional divisor.
Simply because there was only one slope, right?
Exactly. And if you run the Jacobian test on that single point, you will find that the strict transform is technically smooth. The singularity is resolved after just one blowup.
Wait, really? A cusp is fixed instantly.
It is, but here is the fascinating, almost philosophical twist.
Okay, lay it on me.
When you analyze the geometry of the resolved cusp in the newly blown-up space, you find that the new, smooth, strict transform curve lies perfectly, infinitely tangent to the exceptional divisor itself. It
Interesting.
leans entirely against the wall of the new dimension we built to fix it.
Oh, wow. I see the difference. With our node today, the two branches pierced through the exceptional divisor at clean, distinct angles.
Yes.
But the resolved cusp doesn't pierce it. It leans on it. It's entirely parallel to it.
Exactly. So here's the question for you to ponder. If the geometry is technically mathematically smoothed out, but the curve is still leading entirely on the artificial space we specifically created to fix it,
Right.
is the memory of the original singularity ever truly gone? Or is its ghost simply hidden, stretched out along the scaffolding of a higher dimension?
That is a phenomenal question to end on. Have we truly erased the singularity, or have we just hidden its tension in the geometry of the new dimension?
It's something to think about.
Thus and Sigma scholars of Edward Little High, thank you so much for joining us on this incredibly rigorous journey through algebraic geometry. Keep questioning the structures around you, keep zooming in on the blemishes, and keep unpacking the world.